Good morning everybody. Today I will start the second module of advances in welding and joining technology. So, in these modules probably I will try to cover that laser and electron beam welding, and these two processes has been widely used in the welding industry and as compared to the other arc welding processes. So, to start with this module, first of all we will try to look back about the principle of lasers and different types of laser and their applications. So, keyhole formation or conduction mode laser welding processes and that laser welding application and the different materials, and then related to the laser welding we will finally look back to that different laser assisted hybrid welding systems, and finally we will cover the electron beam welding process. So, when we start with the laser principle of laser, we can see that some basic things that we will try to clear out before application of the lasers in the welding purpose. So, actually laser stands for the light amplification by stimulated emission of radiation, and that radiation has been focused on a specific area. Then it is possible to melt that material, and finally that it converts to the thermal energy, and we can join the two materials. It may be either similar kind of materials or different materials, but when we try to that light energy has been concentrated in a very small zone, the heat causes the surface of the material either simply heating or melting the material, or sometimes it vaporizes the material. So, based on that we can categorize the laser welding processes either in the terms of keyhole mode laser welding, or there may be the conduction mode laser welding process. But we know that there is a huge application of the laser. Even if we look into that manufacturing industry, the all other different manufacturing processes like machining, cutting, surface modification and additive manufacturing, heat treatment, there is a huge application of the laser. So, here the laser has been used in this manufacturing industry as a source, and that source can be utilized to heat the surface whenever required, either to melt the surface or vaporization of the surfaces. Apart from the manufacturing industry, if we see, the laser is used in the other technologies also, for example, the measurement technology. So, laser based displacement sensor can be used for the very precision measurement. Then huge application of the laser in medical application, but only different of this laser is the intensity of the light and their concentration, or maybe they are focused into a specified area. There also laser can be used the nuclear fusion communication. If you see that laser printing in the additive manufacturing, there is a laser printing technology, but at the normal printing process also we can use the laser. And if you see the to read the compact discs, and there is also application of the laser, and so many optical dishes, there is a huge application of the lasers, and some barcode scanner also we can see there is the application of the laser. So, laser can be used not only the manufacturing industry, rather it is used for the different other sectors and for the different other technology. But our focus is that how we can use the laser in the manufacturing, and it is very specific to the welding processes. Now, to do that into much details of the application of the laser in the welding industry, probably we can look back that basic structure of the laser or some facts about the laser. So, if you see that there is a from the figure there is a pump that is called laser pump. It may be either diode pump or lamp pump. So, the ray can be extracted from by the pump and then it is focused on the some laser active medium, and that active medium may consist of the different solid state or maybe in the gaseous state. And here the what happens, there is a amplification of the ray laser beam, and that laser beam has been concentrated or maybe well controlled laser beam has passed out from the resonator, and then that laser beam can be used using some lens. It can be focused on the specified zone depending on the requirement. So, if you see the basic components of the laser is the first is the lasing medium. Lasing medium is the provides the appropriate transition and the determines the wavelength of the laser. But of course, it must be a metastable state. But to start before the lasing medium, it is a energy necessary for the population inversion that comes from the laser pump. It may be laser pump, it may be diode pump, or it may be lamp pump. And then the optical cavity, that means within the optical cavity there is a opportunity for amplification and the provides the actually it creates the directional beam and which defined, and actually here the it is the length and the length of wavelength and the transparency has been defined in this zone, and it comes out as a coherent, that means synchronized phase of the light, and collimated, that means parallel nature of the beams comes out from this lasing medium, that means comes from the resonator, and then finally it is focused using some lens. So, basic properties of the laser, if we see that it is a monochromatic, that means single wavelength and the high intensity. So, if you see the high intensity means around 10 to the power 14 watt per meter square. So, when thus this is the from the source, can we see that source can be at the different two basic units, that one is the pump and another is the amplification and the creation of the collimated and coherent laser comes out from the system. So, this is the basic system from we can create the laser light, and then we can use the several application of the laser light. Now, if you see that laser spectrum, specifically overall spectrum, from the figure it is obvious that there is overall spectrum, that gamma rays, X rays, ultraviolet, infrared, microwaves, radio waves, all these kind of waves having some specified wavelength. But laser, the spectrum of the laser operates in the specifically in the ultraviolet, visible, near infrared and the far infrared regions of the spectrum. Now, if we focus on the laser, if we see that laser can be operated at the different wavelength, from ultraviolet to the far infrared. If you see that first is the visible, and visible that ray actually we can see on the eye, and it is not hazardous to the open eye, but the ultraviolet, near infrared and the far infrared is may not be the, it may damage the skin or maybe the damage the eye, but it is necessary to operate the laser within this wavelength. So, I think visible, it is a basically visible length is 400 to 700 nanometer, and near infrared 700 nanometer to 1400 nanometer wavelength can be created. So, looking into the different laser spectrum, there is a wide variability of the laser can be created, and the using the different lasing medium or specifically the different lasing medium. Now, our if we see the mostly use the laser in specifically in the manufacturing process, in very specific to the welding process, that we generally call the NDWAG laser, and that is also called the rod laser, and here we can see the wavelength is 1064 nanometer. Similarly, YB WAG laser, that is the disc type of laser, and the wavelength is 130 nanometer. So, whether we can say the rod laser or the disc laser, specifically in the lasing medium, what type of the shape actually decides this kinds of name. Specifically, rod laser, that solid medium in the shape of the rod can be used in ND-WAG to create the ND-WAG laser, or disc type of thing can be used, shape can be used in case of YB WAG laser. Similarly, carbon dioxide laser also widely used, and that is also in general the gas laser, where the wavelength is around 10,600 nanometer. So, if we see, so there is a huge difference on the ND-WAG laser and carbon dioxide laser, that in the sense that wavelength is in carbon dioxide laser is 10 times more than the ND-WAG laser. So, this wavelength variability actually indicates in applicability in terms of the absorption of the laser when it interacted with the material. So, that is very important. So, that how this laser with this different wavelength interact with the substrate material, based on that we can find out or applicability of the different lasers actually comes out. Now, in general, if we see the characteristic of the laser light, we can find out there are many colors from in normally green, red and some other colors is used, and then many direction. So, it can be focused on the many direction, or the laser, if we do not control the laser light, so it can direct scattered in the different directions, then many phases. So, these are the common characteristics of the laser light, but when you try to use the laser in the different application, specifically in the manufacturing processes, if you see the one color which we choose for a specific application, that one color actually decides the applicability of the laser for the different type of materials or different purposes. One direction, so rather than many direction, if it is possible to focus on the laser light into one direction, that actually relates to the beam energy of the laser. And one phase, if we focused on the one phase of the laser light, that actually correlates with the maximum energy can be delivered to the workpiece. So, among this variability according to our need, so we choose one color, one direction and one phase that specify the typical application of the laser in the manufacturing process. Now, in general, if you see that what way the laser works. So, the mechanism of the energy transfer in case of laser welding is completely different from the arc welding process. And of course, the absorption of the energy depends on the how laser is interacting with the material. That means, in general we call the laser matter interaction. And laser output actually not electrical in nature, that means it eliminates any effect of the magnetism, but this is not the case in case of arc welding, because arc welding normally there is a current flow and it always try to create some electromagnetic field, and that arc characteristics or maybe creation of the arc mechanism is different from the laser in that sense. So, here laser is not required any electrical current. So, that means this laser welding process is not limited to only electrical conductive material. So, that is why that is the beauty or advantage of laser using any kind of materials, whether it is electrically conductive or non-conductive. So, but that limitation also exists in case of arc welding process. So, to create the electric arc, the material should be the conductive. Now, other point of the advantage of the laser welding process is that it do not require a vacuum, and also it does not produce any X-ray like electron beam welding process. So, laser welding can be done without a vacuum, and but normally in case of laser welding process we use the shielding gas to protect the molten metal from the outside atmosphere. So, these other two advantages, that not required vacuum and it does not produce the X-rays, that is the typically advantageous with respect to the electrical electron beam welding process. So, in that respect it is advantageous, and it at the sense it is the cost of the laser welding process is less as compared to the electron beam welding processes, but it is advantageous with respect to the arc welding process, because laser welding the laser beam energy can be focused into a very small area. So, high depth of penetration can be created using the laser, which is not which is very difficult by the electric arc welding process. So, in that respect laser welding is advantageous with respect to the arc welding process. Now, there are several types of the lasers and designs of lasers typically, and it is day by day there is a increasing use of the lasers, designs of the lasers are also come out. So, but normally if when you try to use the laser, that we can categorize in such a way that one is the solid state laser. So, solid state laser, basically the crystalline glass or rod in the lasing medium which is doped with the ions, and that ion doped with the ions, and actually it provides the required energy state. So, neodymium is the common dopant in various solid state laser crystals, including yttrium, aluminum, garnet, that is the full form of the YAG that we use the WAG laser. So, in this case the solid state laser, normally we use a dopant material we doped with the ions, so that it actually helps to provide the required energy states, and that ray can be used by the including the yttrium, aluminum, garnet to produce the rays. So, solid state laser is basically the laser amplifiers where the light is guided due to the total internal reflections, that reflections happens within the one single optical fiber that are called basically the fiber laser. Of course, fiber laser is a solid state laser, but in this case the only difference in the with respect to other, that optical fiber can be used to guide to conduct all the internal reflections. So, in that sense the fiber laser is the with respect to the ND-WAG laser, or with respect to the other solid state normally use the solid state laser, the concentration of the light can be more in case of the fiber laser. Other type of laser we see the gas laser, and we use the commonly CO2 gas lasers or helium neon laser. So, here the lasing medium is the gas. Now, apart from the another, that if we look into that type of the fiber laser, here if you see the fiber laser, actually rare earth element such as yttrium is doped into the core of an optical fiber. So, in this case the laser emission, basically emission of the light actually within the fibers using a semiconductor diode as a light source and delivered through a flexible optical fiber cable. So, that is the beauty of the fiber laser. So, that within the fiber the total internal reflection is controlled, and finally it is delivered also using a fiber cable. Fiber lasers having monolithic entirely solid state designs, and that does not require any mirrors or optics. So, like if you see that most of the cases when you try to produce we need the mirror to produce the laser beam, but that is not the case in case of fiber laser. Another type of disc commonly used, that is called disc laser. So, thin disc laser, actually the pumping we use the diode pump and it is also a solid state laser where the gain medium is a laser crystal. So, in the lasing medium we can use a laser crystal here. So, typically YB that means yttrium aluminum garnet from here in the type form, not in the form of a rod, rather than that solid, that shape is like a thin disc. So, that is why it is called the disc laser. So, of course, Nd:YAG laser, it can be the amplifying medium can also be the disc, but in this case a shorter emission wavelength is generally produced in Nd:YAG laser. So, the shape of this lasing medium, that means solid state medium, is in the form of the disc, that is why it is called the disc laser, and this thickness of the disc usually is much smaller with respect to the focused with respect to the laser beam's diameter. So, disc laser is having the considerable advantage in the sense that it is a ability to cool very effectively, and power and pulse energy can be controlled or can be scaled up as a very higher values than rod laser, or maybe in general we can say that Nd:YAG laser, or with respect to the fiber lasers, or with respect to the geometric shape of the solid state medium like slabs. So, this is the typical advantage of the disc laser, and of course, easy to scale power, increasing that by simply increasing the diameter of the pump area of the disc, and but in this case its trade off is equal to, there may be the, if you try to scale up of the power, there is a decrement of the beam quality. So, that kind of trade off is required, either increasing the pump area and decreasing the beam quality. So, apart from the disc laser, other type of laser is the diode laser. Most commonly used the diode laser if we see, but nowadays it can be used readily if we see the several domestic CD player, optical communication, laser printer, laser pointers, we can see the application of the diode laser. So, one advantage is the diode laser, it can be formed in a very compact form, but if commonly we use the diode laser in the CD player, optical communication, laser printer, the intensity of the laser is less, but at the same time it is possible to use the diode laser even for metal cutting processes as well as welding processes, that is called the high power diode laser. So, the main advantage or attractive nature of the diode laser as compared to the other laser is that it can be produce the extremely compact form, and it is easy to carry and ease of operation, and we can easily apply it any local local manufacturing or modification of any locally. In that case, probably diode laser is a good solution. Now, we look into one typical laser that is called Nd:YAG laser. Most commonly we use the laser in the several applications. Now, if we try to characterize this type of laser, we can see that type of the laser, doped insulator laser, that means the neodymium is the dopant here, and active medium is the yttrium aluminum garnet, that is the also of course this is the solid state laser. Then active center neodymium. Pumping method, we use the initial laser light, that by using the optical pumping, and pumping sources and the flash pump, that is called xenon flash pump, generally used for the as a pumping source, and the optical resonator, the ends of the silver coated, the rods are silver coated, and two mirrors, partially and totally we put the two mirrors, so that partially and totally that acts as a reflector, and finally the beam is produced beam is directed in specific direction. So, typically this Nd:YAG laser having the laser power of output power of around 20 kilowatt maximum, and the nature of the output can be produced is a pulse laser. So, pulse laser means not the variation of the pulse energy with respect to the time, and then the final wavelength for this Nd:YAG laser is 1.064 micrometer. So, this all type of critical information for the Nd:YAG laser, which is most commonly used in not only in welding, this laser can be used for other manufacturing processes also. But if you see the laser sources in welding process, another mostly used lasers, that CO2 laser, but apart from that most commercial lasers that used for welding purposes, we can categorize into that. First one, the CO2 laser, Nd:YAG laser, but Nd:YAG laser either can be lamp pumped or laser diode pump. So, laser diode pump means electrically pumped semiconductor devices. So, then disc laser and diode laser, and finally, the fiber laser. So, all these 5 different types of the lasers is normally used for the welding purposes. If you see the typical characteristics of the CO2 laser, that here if you see that wavelength is around 10.6 micrometer, but it is in that laser spectrum in that range of the far infrared ray, that is the wavelength of this CO2 laser. Laser media CO2, N2 and helium mixed gas, and average power maybe can produce the 45 kilowatt maximum power it can produce, but power continuous wave normal power around 500 watt to 10 kilowatt, and merits means is the easier higher power. So, in carbon dioxide laser it is relatively easy to gain the much power. When there is a much power needed, probably you can use the carbon dioxide laser, but efficiency is very low. In this case efficiency is around 10 to 25%. So, if you see the overall idea of all this type of laser, and then when it may be applicable in the different welding purposes, first one is the carbon dioxide laser. Of course, carbon dioxide laser, when there is a high power requirement is there, probably we can use the carbon dioxide laser, and since the carbon dioxide laser wavelength is 10 times more than the Nd:YAG laser. So, focused beam diameter and absorptivity of this laser is different from other type of laser. In that case, Nd:YAG laser can be useful when when there is a more precision is required in the welding process, or maybe very thin sheet. It is possible to use the Nd:YAG laser in general, because Nd:YAG laser the wavelength is in this case is 10 times less than the carbon dioxide laser, and also it is possible to focus Nd:YAG laser into a very small zone as compared to the CO2 laser. But in that respect, the disc laser, diode laser and fiber lasers also having certain advantages, but nowadays if it is possible to high depth of penetration is required with the very narrow heat effector zone, then fiber laser is a good solution for that. Disc laser and diode laser is used some other purposes. So, if you see overall that by knowing the fact about the laser and the different type of laser and the principle of operation of the laser and the applicability of this laser in case of the welding, we can find out different advantages and disadvantages of the laser when it is applied to the welding process. So, if you see the several points, first point is that very good metallurgical properties can be achieved in the weld using the laser welding processes, but this is the very good in the sense that it is relative to as compared to the other typically the electric arc welding processes. The heat affected zone is very narrow, probably in this case the in laser welding process the heat affected zone is very small as compared to the other arc welding processes. Aspect ratio, that means depth to width ratio, the weld depth of penetration and the width of the weld zone, that ratio probably it is possible to produce in case of laser welding process, it is relatively higher as compared to the other welding processes. So, it can be achieved that as the 10:1 using the typical. For example, if we use the fiber laser, probably we can achieve this kind of depth to width ratio. Another point is that focused laser light. So, concentration of the laser light in the small zone is very high in this case. So, that means it can produce the high energy density over a small zone. So, that is another advantageous if we want to reduce the heat affected zone by the laser, then by any other of the welding processes, probably laser is one of the good choice, or I think laser is the best choice in this case as compared to the other welding processes. So, and what is another, the laser welding can be used even at the room temperature. That means that may not be necessary to produce any the preheating of the sample to produce the welding. Next is the no vacuum chamber is required in laser welding processes, and it does not produce any X-ray. That means during the operating of this laser welding process, there is no X-ray shielding is required, but these 2 points, vacuum chamber and X-ray, that is advantageous as compared to the electron beam welding processes. But apart from the several advantages of the laser welding processes, having some also demerits of all this process. First thing is that since laser is focused in a very small area, and most of the cases we use the laser source at very high speed, when the laser power density is very high or energy density is very high, it can be used for welding purposes at very high speed. But to do that, there is a negative point here, is that rapid cooling normally we found out in case of laser welding processes, that may cause the cracking or maybe other metrological incompatibility during the welding process. So, maximum joint thickness, another advantage is maximum joint thickness that can be welded by the laser source is somehow limited. So, that actually depend on that power density of the laser and the focused beam diameter. Accordingly, we can decide whether we need any conduction mode laser welding process or keyhole formation is required in this case. But this disadvantage is, but of course, the high depth of penetration can be produced by laser welding processes as compared to the, it is advantageous as compared to the other arc welding processes. But if we use the electron beam welding process, so we can produce the more high depth of penetration welded as compared to the laser welding process. So, in that sense, the depth of penetration is limited in laser welding processes as compared to the only electron beam welding process, but not as compared to the other arc welding processes. Third point is that high reflectivity and high thermal conductivity of the material, of course, like aluminum and copper alloy is very much difficult or to do the welding processes using as a laser. Of course, in general this welding of the high, I can say that difficult to weld material like high conductivity and high reflectivity material is really difficult using the not only the laser welding processes, in other welding processes also as well, but still there is a scope of doing the good weld in case of laser welding process when you try to use the pulse welding processes, and then when you use the control the shape of the pulse, in that case that high reflectivity or difficult to weld materials is possible to do the weld using the laser welding process. We will discuss the effect of the pulse shaping for the difficult to weld materials later on. Some weld porosity brittleness can be achieved and it is due to the rapid solidification, that is another disadvantage of the laser welding process. But main disadvantage of the laser welding process is the normally CO2 laser or ND-WAG laser, the process energy efficiency or energy conversion efficiency is relatively very low. Maybe you can say that around 30% or less than 30% in this case. So, apart from the several advantages and disadvantages, there is a development of the laser welding processes and the typically the keep in mind in the application of the different type of the materials. But before looking into that, we can little bit discuss or recap the laser beam optics. So that get the idea that how it can be used or how this laser can be used for the welding purpose. So, first thing is that application of the laser beam is basically focusing, modifying and of the laser beam shape, and but shape of the beam is laser typically follow the Gaussian distribution, and that ideal Gaussian distribution profile can be represented as that is called TEM 00 mode. So, that means laser can be represented in the different mode. So, ideally representation is the TEM 00 mode. So, Gaussian intensity profile means that intensity of the laser energy distribute in such a way that when it is focused on a substrate material at the center point, the intensity is maximum, and that gradually it is decreasing towards the boundary of the focused area. So, that is typically represented by the Gaussian distribution. Now, if we see from the figure that there is a collimator lens and the final focused lens is given within the laser. So, laser comes from the fiber cable and the collimator lens is given, that is that laser when it comes out and then laser ray becomes parallel reflecting, and then optics another lens is there, second lens, and second lens is mainly used to focus the laser beam on a specified position. There is a final focus. Now, in this case, this is the typical laser optics we generally use in the laser beam welding process. But if we in general if we see the short focal length, that means if focal length is the very short when you focusing on the workpiece, then laser can be used the faster weld speed. That means because when the laser is focused in a very small zone, the laser intensity increases. So, to balance the amount of the energy, this laser can be used in the very high speed. And other thing is that if laser is focused on the short things, then short focal length actually can be used the less heat input in the form of a less heat input. But a long focal length, that means the longer depth of focus, and that is also actually in other long focal length, of course, it decreases the intensity, but the advantage is that it can be safer side when there is a formation of the weld spatter and the smoke. That means lens is that source is a long distance, that it may not be subject, it may not be get rid of the weld spatter and the smoke from the workpiece material. Now, with this laser optics, probably we can find out, suppose there is a core diameter, this is the fiber cable, the core diameter is DC here, and the focal length for this lens is fc, small fc, and the focal length of the focusing optics, this one, suppose this focusing optics is f0. So, the final spot size fs can be estimated as the ratio of the two focal length of the lens fc by f0 multiplied by the core diameter of the fiber. So, that means that by changing this focal length, probably it is possible to estimate the focusing final spot size of the laser when it is focusing on a specific workpiece or the substrate material. So, this simple calculation shows that the final spot size can vary depending upon the core diameter and this two focal length of the lens. If we see the other critical term which is the laser beam optics, that is the m square. M square is the represents one parameter, the deviation of the laser beam from the theoretical Gaussian. So, theoretical Gaussian module we represent the laser beam intensity, that is called the TEM 00 mode, but the measure of the m square actually decides that how it is deviated from the ideal TEM 00 mode. So, m square equal to 1, that is that represents the theoretical Gaussian TEM 00 mode. This is the very ideal case, and but m square can vary between 1.1 to 1.7 specifically for the diode laser, and for high energy multi-mode laser m square can be as high as possible, maybe 25 or 30. So, m square is the parameter that actually decides how the laser beam is deviated from the Gaussian mode, that means TEM 00 mode. So, if from the figure if you see the laser irradiance and the distance. So, at the center the laser intensity is maximum and gradually the intensity actually decreases with respect to the center. Now, several laser modes can be observed or maybe we can say that several modes can be created for the different application. If you see the modes, the TEM 00 mode and the color contrast of the TEM 00 mode, it indicates that at the center the laser intensity is very high, maximum, and then towards the outer periphery the intensity is gradually decreasing. So, other modes can be created in several ways, that TEM 01, it is a multi-mode, and another TEM 10, also the shape and the modes are different, shape are different here and the different other mode. TEM 11, there are multi-mode, and TEM 02. So, this type of modes can be created depending upon the different application of the laser. Now, if you look into further laser beam optics, that this is the laser source and it is the diverging, but laser source is actually not is a point source, it is a sub diameter, that planar wave front can be created at a specific diameter size, that is 2 omega w 0, and that is called the where the beam wave front is flat, that is called the beam waist radius equal to w 0. So, here it is w 0, and the Rayleigh range means where the beam radius spreads by a factor of √2 and wave front curvature is the maximum. So, it is a wave front in this zone, wave front is almost flat, but here the wave front curvature is almost, here wave front curvature is the maximum. So, that is called the from z equal to 0 to z equal to ZR, that is called the Rayleigh range. So, waist diameter, that is the where the wave front is the flat, then beam waist radius is basically omega 0 or diameter equal to 2 into w 0. So, similarly, here it is the beam waist diameter, that is the 2 w 0, and here you can see that from 0 to ZR, that represents the Rayleigh range in this case. But here planar wave front we can find out, but had z equal to infinity and theta equal to beam divergence half angle. So, these are the typical optics or optical parameter we generally consider for the to analysis of the laser beam. So, here ZR is having some relation with the wavelength of the laser, ZR equal to pi omega 0 w 0 square by lambda and theta equal to lambda by pi w 0. So, these are the relation between the half divergence beam angle and what is the Rayleigh range in this case, or Rayleigh length in this case, in terms of the wavelength of the laser and the waist beam diameter of the laser. Now, there is another parameter that actually represents the laser beam quality, that is called the beam parameter product, or in general we call the BPP. So, of a laser beam is defined as the product of the beam radius and the beam divergence half angle. So, the usual unit are millimeter times milliradian. So, that is called rad. So, this is the unit for the beam parameter product. The BPP is basically used to specify the weld beam quality, and in general the higher the value of the BPP, then lower is the beam quality. So, apart from this parameter of laser beam quality, let us look into one example for on the laser beam optics. If we try to look into the example that determine the diameter of the local spot for 10 millimeter focal length lens to focus collimated output of a helium neon laser having the wavelength is equal to 632.8 nanometer and that has a 1 millimeter diameter beam. So, assuming the divergence angle is small and the laser is a point source. So, to solve this parameter we can find out the half beam divergence half angle is the focal length, that is the focal length and the at the value of the that laser beam. D is the diameter of the lens. So, D by theta equal to can be estimated D by twice f. D equal to has the diameter of the lens and f equal to focal length of the lens. Now, depth of focus is estimated at the point of maximum curvature, that means at z equal to zr. So, in this case theta is simply estimated in terms of the laser wavelength lambda by pi into w0, and from here theta equal to this and that is another equals theta equal to d by 2 f. From these two approximation we can find out the relation d by 2 equal to lambda by phi w0. So, from here we can find out the twice w0 equal to 4 lambda f by pi d. So, all the parameters are given, the wavelength and I think f also given and the diameter also, beam diameter also given and pi values we know. So, based on that we can find out the diameter of the focal spot should be twice w0. Now, apart from the beam optics, it is also necessary to know that different pulse characteristics or how we can represent the pulse in case of laser process. So, because there is a huge application of the pulse laser in the welding process. So, pulse characteristic can be represented from the figure. If you see, there is a single pulse, that means over a specified length of the time, that is called pulse on time, the total energy of the laser is released, but it can be repeated over a cycle. That means cycle time also important to know here, another parameter, or we can say that pulse frequency or pulse repetition rate in case of a laser welding process. So, that parameters in this case, if you see the average power, pulse repetition rate, which is represented in terms of hertz cycles per second, or pulse repetition rate and a pulse frequency are the same here, and another important parameter of the this is the pulse energy. So, from the figure if you see that it is not necessary that energy will be released in the, that is the shape, temporal shape of the pulse. So, that temporal shape of the pulse may not be in kind of rectangular shape, but some we can say that some other kind of, maybe you can say that it is a Gaussian kind of shape. In this case, that it is represents that half width half max, full width half max, sorry, full width half max. So, in this case the half power at the center and the peak power. So, in between the half power, at the half power point we can find out that the what is the duration of the pulse, so that total energy can be balanced. It is represented in concept if you consider as a one rectangular pulse. So, in that sense we can find out the full width half max, that duration of that time is basically the pulse duration. So, that pulse duration can be represented Ton, that is the pulse duration at the full width half maximum points, that is the pulse duration. So, here we can find out that area of this temporal pulse is represents basically the pulse energy. So, that is used by EP. So, now energy per pulse can be estimated that multiplied by the pulse repetition rate or pulse frequency, and that actually indicates the average power. So, average power is basically equivalent to, if we assume it is a continuous mode of the laser welding process. So, that if you consider there is a continuously application of the pulse energy over the whole duration, that actually represented by the average power. But peak power, what is the maximum power for the pulse? In this case we can find out the P maximum into laser on time, that is equivalent to the pulse energy. From that point of view we can find out the what is the maximum power. Now, if we look into two examples that of the pulse characteristics. Example 1, that in endoarc laser The measured parameter are the pulse frequency 10 kilohertz and the average power equal to 4 watt. Then what should be the pulse energy? So, in this case simply we use this formula that the energy of a pulse into pulse repetition rate, that actually represents the average power. So, from here we can find out that the pulse energy is equal to average power divided by the pulse frequency or pulse repetition rate, that actually coming out the 0.4 millijoule in this case. Now, if you see that if the laser measured powers or pulse energy is 5 millijoule and the pulse duration equal to 10 microsecond. So, what will be the peak power? So, in this case we can find out the maximum power into pulse on time equal to the pulse energy, and from here we can find out the maximum power equal to 500 watt. So, here we can see that if pulse energy is 5 millijoule, in this case the maximum power is the 500 watt, and if you see the another first example, here if we see that actually the average power is 4 watt, but peak power is 500 watt. So, that means if there is a, if we assume that if we neglect the effect of the pulse, then we can assume that the energy source used as a continuous power of the 4 watt. Rather we can say energy source can be used at the pulse source where the peak power can reach up to the 500 watt. So, there is a huge difference in the average power and the peak power. So, that difference in case of pulse laser, the peak power and the average power difference can impact on the manufacturing process, and that we will try to see the, if we look into the effect of the this pulse shape and the pulse energy specific to the welding processes. Now, if we come to that, process parameters for the laser welding processes is that in general, that is first is the pulse energy, then power density, and then we estimate the m square, that is that actually defines the measure of the energy distribution. So, what way the energy distribution at the different mode of the laser, then pulse duration and the frequency, peak power, what is the peak power of this laser, and the spot size and laser scanning speed, that means applicable of the, when we apply the laser, in what velocity the laser has been moved. So, all these are the typical parameters for the in case of any pulse laser welding processes need to define, and that all these parameters actually decides the applicability of the of this laser and the two different manufacturing processes, and of course, the different size of the workpiece. Now, primary controllable parameters, the main control parameters in case of laser welding is that laser beam energy output. So, specifically pulse laser welding process, the main parameter is the pulse energy output and the duration of the pulse over which this energy has been applied to the substrate material, and that is required to define the pulse laser source. And second is that laser focus, that means where the laser has been focused on the surface or the below the certain depth from the top surface, accordingly the laser beam radius can be estimated, and that actually radius decides the heat affected zone or molten zone will be created by application of the laser. So, that are the two primary controllable parameters in case of pulse welding processes, and other parameters increasing voltage, that means deeper penetration with less melting, that is also if the there is a deeper penetration with less melting is required, then need to increase the voltage of the applied laser. Then if deep and wider melting is required, then probably duration of the pulse is we can increase the duration of the pulse, and if we use the shallow and soft penetration and wide beam is wide shape of the weld zone is required, probably we can increase the beam diameter. Then that means by increasing the beam diameter with the heat affected zone or molten zone can be increased considerably, but with the compensation of the decreasing the depth of penetration. But both increasing the voltage as well as the pulse duration, in that case very deep melting or is required, maybe in that case the weld pool volume is requirement is very high, then we need to operate both the increment of the both voltage as well as the pulse duration. Now, apart all these parameters, process parameters are need to define in any case of manufacturing process, not only in the welding processes, but measure laser beam capability actually depends on the how it is propagated with the as low as low divergence angle, and specifically focusing in the very small zone by the lens. These are the two parameters that actually indicates that the laser beam quality. Of course, laser beam quality measured by the m square or either m square value or the BPP value. So, that ratio of the divergence to the actual beam to the theoretical diffraction limited beam, that is the measure of the m square, and the m square tend to increase with the increasing the laser power. So, basically m square decide the different mode, and the BPP the quality, that means its BPP measured in terms of the laser divergence angle. So, all these parameters are very much sensitive in any case of manufacturing process when you try to apply the laser as a source. Now, we come to that point mostly used, that conduction mode and the keyhole mode laser welding processes. This is very important part of the laser welding process. First is the, if you look into the figure, you can find out the difference, what is the conduction mode, what is the keyhole mode laser welding process. So, that figure, this figure indicates that here application of the laser on some substrate material, there is a, it produces the shallow or wider width and the very small penetration. And other cases, if you see, there is a laser beam actually deeply penetrating the substrate material. So, first case is the conduction mode, because there is no vaporization loss of the material, and second case the laser beam inserts and there is a definitely there is a vaporization, it reaches the maximum temperature in such a way that it vaporizes the substrate material, and that is why it interact with the material and it forms the kind of keyhole formation. So, these two modes depending upon the application or that mainly variation happens into the as in the source in terms of the laser power density. So, if we find out the conduction mode, typical characteristic of the conduction mode laser welding process, the power density is basically less than 10 to the power 6 watt per centimeter square. So, this is the threshold value. We decide whether it is conduction mode or the keyhole mode laser welding by simply measuring the power density of the laser. So, power density can be estimated by the laser power divided by the area of the cross section over which it is falling. So, in conduction mode, simply heating the workpiece above the melting temperature, but without vaporizing the material. So, penetration is controlled by the conduction mode only, there is no formation of the any keyhole. But keyhole mode, if we look into other cases, the laser power density always exceeding the 10 to the power 6 watt per centimeter square, then normally it produces the keyhole. So, molten metal actually starts to vaporize and actually forms a vapor domain there. That means, by opening up a blind hole, that is called the keyhole in the molten material, and the vapor pressure from the hot metal keeps the molten open the molten pool during the welding processes. So, once the moves away the laser source from that point, then again that cavity actually filled by the molten pool, and afterwards it solidified and gets the welded joint. So, increasing the energy efficiency, that is another advantage that in keyhole mode laser welding processes, that when there is a deep penetration of the laser beam inside the workpiece material, the absorptivity of the metal actually becomes absorptivity of the laser by the metal is actually increases. So, that means in this case the energy conversion efficiency or maybe efficiency of the process, welding process, due to the multiple reflection within the cavity, in general it is increases. So, these two modes are, it is very important to identify the which modes of welding process is used and when we apply the laser source in the in any welding of the any materials. Now, apart from now we come that we see that difference of the two conduction mode, the keyhole mode laser welding processes, both the cases that stainless steel has been joined using the laser welding processes. So, first that if you see the first figure, there the dotted line actually indicates the fusion zone and next line indicates the heat affected zone. So, this molten zone, it seems the depth, that ratio depth of penetration and width is less in this case, and second case if you see that there is a high depth of penetration of the weld pool, but width is relatively less in this case. So, first case we can see that from the macrograph itself we can see that it is generally conduction mode laser welding process. So, what are the typical characteristics is that low welding depth, small aspect ratio, that means penetration and width ratio, low coupling efficiency, very smooth, highly aesthetic, and the weld pool can be appear in case of conduction mode laser welding process. These are the typical characteristics of the conduction mode laser welding processes. Now, if we look into that next one, that keyhole mode characteristics in this case, that high welding depth, you can produce the high welding depth, high aspect ratio and the high coupling efficiency. So, here if you see, but this weld pool has been measured after post weld treatment, after post weld, that means after the solidifying the molten zone, and then we take the macrograph and we estimate, we can visualize the size of the weld pool during the welding, but the size of the weld pool does not ensure the size of the keyhole. Keyhole probably it was that marked by the yellow color, that probably was the size of the keyhole, and with that keyhole size, that means we can, the keyhole size means that was the vapor domain during the welding processes, and remaining is the it was the molten zone. So, there you can see the conduction and the keyhole mode laser welding processes, there is a wide difference in the weld pool shape and size, but conduction mode is normally used for the very thin sheet and foil, whereas the keyhole mode can be used the much high thickness materials is supposed to join in that case. Now, we can see the laser welding of the metals. Here see that what are the typical laser welding for the metals, that heat flux is used from the heat sources, but in this case is the heat flux means in the from the laser source we can use sources. Then localized melting and solidification occurs. Of course, localized melting and solidification occurs means when there is a laser is at one point, specifically in case of spot welding process, then when you switch off the laser source, then after that it solidifies. But in case of the linear welding process, when we use the moving laser source, so when laser moves away from the actual focus on the workpiece, then after moving away is subsequently the molten material actually solidify. So, that each point of the joint for a linear welding case, that it is subjected to some localized heating and then again solidification of the material. But one point is that, of course, whether we use the conduction mode or keyhole mode laser welding processes, all the cases, there is within the small weld pool, there is a flow of molten metal may happen. It may be either laminar flow or maybe the turbulent flow of the material may happen, but most of the cases we find out specifically in the laser welding process that it is a turbulent flow, or it is very difficult to identify or characterize whether it is a laminar flow or turbulent flow of the material. So, anyway, there must be some material flow during the welding process. So, that means during the welding process the material was not stationary, there is a flow, it flows on specific direction. We will discuss later on the flow of the material, but finally happens the after the solidification, there is a due to the different thermal expansion and contraction that actually finally produce the some amount of the distortion in the welded joint as well as the some amount of the residual stress. So, this cannot be avoided in any case of the welding processes. Now, if we characterize these things, the welding processes in general, there is a source of the heat, that means in this case the laser. Next, it creates the fusion zone and as well as it creates the heat affected zone. So, right hand side figure shows the one typical example of the laser spot welding. So, that is the simulation of the laser spot welding. So, molten, the red color actually indicates the molten zone. So, initially the initial time was very less. So, it creates very small oil pool, and with the application of the further time, gradually the molten pool size actually increasing. The remaining other is the color indicates the heat affected zone. So, within the in the simulation process actually the apart from the red color, the other different color we can produce the contour isotherm, and that means constant temperature. That temperature actually indicates the heat affected zone in case of the laser welding processes. Now, of course, the laser welding process, it is always subjected to some material flow, but what are the driving forces for the material flow in the laser welding processes? So, material flow mainly happens due to the buoyancy force, because there is a temperature difference, and of course, we takes into account the density differences through the buoyancy force. And another point is that surface tension, that means when the surface of the molten pool is interact with the another medium, in between that media it produces the surface tension force. So, depending upon the material and the next, because the molten pool is basically is covered with the shielding gas. So, that interaction between the molten pool and the shielding gas in that surface, there may be the different surface tension force it can be create. So, depending upon the composition of the material, the surface tension force acting normally from center of the heat source to outward periphery, or it may act the reverse direction from outward periphery to the center. It depends on the composition of the material. So, we can do the similar kind of simulation. We can see the colored figure that actually the within this red zone that indicates that molten pool. So, within the molten pool there may be some must be some heat conduction, but at the same time that there must be some material flow, and the arrow actually represents the material flow field within this zone. And if you see that there is a non-symmetric profile looks like, and when in this case the laser source is moving from one to another direction. So, it creates at a certain instant of time. So, it creates the molten pool certain area, but other part is already solidified during the welding process. Now, further zoom this thing material flow, if you see in this case that the material flow creates that in such a way that from the center to out, that actually driving force, the surface tension force is basically acting from center to the outward periphery. So, it creates the clockwise material flow field, right side, left side we can say the anti-clockwise material flow field. So, in this case the anti-clockwise, and right hand side is the clockwise. See the depth direction also we can see that other cases. So, this is the first cases. So, in the second cases if you see the material flow, the right hand side the flow field is basically acting in the anti-clockwise direction, and left hand side there is the clockwise direction. So, in the difference between these two cases, the second cases the material flow actually helps to produce the high depth of penetration, but in the first case the weld width is very high, but depth of penetration is low as compared to the second case. So, here the difference is only the nature of the surface tension force, and that actually drives the nature of the material flow, and finally, the nature of the material flow actually decides the size and shape of the oil pool. So, second cases there is a certain percentage of the or that surface active element, presence of the surface active elements actually revert the surface tension forces, and that actually in effect it actually increases the weld penetration and decreasing the weld width. So, that is why fluid flow or metal flow is important to analyze in the certain cases when there is a presence of the surface active elements, and that works adverse effect to increase the depth of penetration. And one important point is that of course, the metal flow happen here is the buoyancy force and only the surface tension force, but in case of arc welding process the driving forces for the materials should be included the electromagnetic force that actually influence the metal flow field as compared to the laser welding processes. So, apart from the laser welding process of the different materials, maybe now we can look into that pulse shaping in the laser welding process. So, pulse shaping is advantageous in the sense that steady state pulse to overcome the some inherent problem during the joining of the materials. The shaping pulse shaping of the millisecond pulse basically is estimated based on the practical application of these things. Simply pulse shaping means we understand that temporally distribution of the energy within the single laser pulse, but modulation of the suitable pulse basically if we create the different shape of the pulse from the laser source, that actually helps to weld of the or to applicability of the laser for the different purposes. First thing then is the modulation of the pulse can be done with the aim to that by to optimize the penetration depth. Welding of the very high reflective materials decides the mode of the welding, that means whether it is keyhole or conduction, and it is effective for the crack sensitive materials. So, right hand side figure if you see that this is the laser power and this is the time. So, here you can see that this is the different temporal shape of the pulse. So, each are having shape of the pulse actually influence to the different welding processes, that means different welding processes for the different type of materials when there is some difficulty. So, difficulty in the sense that very difficult to weld material, simply shaping of the pulse actually helps to get the good weldability of that material. But before do that need to know that what are the different phases of the pulse shaping. That shape of the pulse, how it helps basically, first is the initiation of the melting. Shape of the pulse is a very high energy for the reflectivity material. So, initiation of the pulse actually initiation of the melting by the shape of the pulse, then starting to grow the melting, that can be controlled by the shape of the pulse, stabilizing the weld between the materials, and finally cooling down of the weld. So, all this basically phenomena can be controlled by the different shape of the pulse. Let us see what are the role, what are the different shape of the pulse, how it influence to the different welding processes. So, in case of pulse shaping in laser welding, that first if we see the power is varied over the pulse time, that is true. Now, first figure the crack sensitive materials, and we can design the shape of the pulse like this, but how it helps? The initially upslope at the beginning, that actually prevent the thermal shock. So, not actually application of the energy instantaneously. Laser the gradually or making some slope means that not we are applying the laser pulse energy instantaneously. So, that slope actually prevent the sudden thermal shock. At the same time, down slope at the end, that actually control the cooling. If there is a slope, application of the laser pulse, that actually controls the cooling. So, this typical shape of the pulse is helpful for the crack sensitive materials. If we see the large tolerance, the gap between the two joint materials, there is a existence of the large tolerance. In that case, initially low peak power is followed from the shape of the pulse, that actually helps to melt first material and then the second material, and then increment of the pulse, increment of the amount of the pulse energy over a certain period, and finally very low amount of the pulse energy. So, that actually reduced the stable the melt pool and the basically cool down of the molten material. So, this typical shape of the pulse actually is useful for the large tolerance when there exists some large tolerance between the two workpieces. Next is the high peak power, that actually to start melting. Initially this pulse shape is basically for the high reflective material. So, here the initial the high reflective material we follow without any slope, the instantaneously there is a increment of the amount of the pulse energy, that actually helps to start the melting specifically for the due to the high peak temperature. Although they are high reflective material, so we amount the more amount of energy that helps to melt the start at the starting. Then we reduce the power gradually step by step. So, then molten material absorption rate actually increases, and then finally we reduce the power very small, but we reduce the power is rapidly, not gradually. So, this specific type of the shape of the pulse is very useful in case of the high reflective material. So, we can see that although there is a difficulty of the difficult to weld material by other welding processes as well as laser welding processes, but laser welding process is advantageous in the sense that it is possible to control different shape of the pulse, and we can improve the weldability of the different type of materials like the crack sensitive materials or high reflective materials or sometimes the high conductive materials. So, in this case it is necessary to design the specific shape of the pulse. Thank you for your kind attention. So, next we will start with the laser assisted the hybrid welding processes.